we have Dr. Sone from the University of Wisconsin Madison Geological Engineering Department speaking. He works with experimental rock mechanics and geomechanics to solve problems in fault mechanics, reservoir mechanics, and tectonophysics. Today's talk will be about thermal breakout technology and how heating the borehole can lead to better stress determination. And with that, I will hand it off to Hiroki.
Okay, yeah, thanks for the introduction, Casey. Can everyone see the screen right now?
Yep.
Okay, all right, so I have I'm gonna try to switch between a video in the middle, so we'll see how good it works, but are you guys seeing the presentation or the presenter screen right now?
I'm seeing the presentation.
Okay, good. Okay. All right, so it seems like it's working. All right, well, thank you. So yeah, today, thanks for inviting. It's quite an honor to be invited and present to people who have similar interests. So today, as Casey mentioned, I'm going to talk about laboratory and field validation of the thermal breakout technology. So this is what I present today is by no means just my work. Really, it's a collaboration with the RISPEC company located in South Dakota, members from UW-Madison, also with the Lawrence Berkeley National Lab, and also a company called Integrity In-situ, and some technical advisors, Thomas Stowe and Dan Moose. And it's a 4-year project where we are now in year 3, and this is funded by DOE National Energy Technology Lab. So basically, the idea is that we're trying to kind of build a methodology for measuring stress. Okay, so introduction. So I'm going to talk a little bit about, I think with today's audience, maybe you may not have to go too much in detail, but why we care about in-situ stress, how we have measured it, and then what is our concept, and then some proof of concept studies that we did in the field in the lab, and then a little bit more in-depth technology validation, which is the experiments we did in our lab. Okay. So first, talking about why we care about in-situ stress. So I think probably for many of you it's familiar, but just to make sure we're on the same page, in-situ stress, understanding it is of course very important for geomechanics. If we want to optimize recovery from unconventionals or geothermal, we need to understand when microseismicities or faulting happens and the associated dilatancy. We also need to, if we're trying to store fluids in the earth, like carbon or nuclear waste, we also need to understand to what extent we can keep injecting, and that's also governed by stress. More on the shallower side, here's just an example of kind of a interesting photo I found about, I think that demonstrates mine stability as an issue. Obviously this one is, well, they're pretty relaxed, considering how severe the situation is. But if you want to predict these, you also need to know stress. Also from the larger scale earth science story, we need to understand stress to understand earthquakes that pose hazard risk to us. So how have we measured stress in the earth? There's many technologies that we've been using. On the left is kind of representing the more geotechnical engineering side of this in this list of techniques. For instance, people have put flat jacks in rocks, slots that they cut into the rock. What they do is they pressurize the rock until the they deform back the rock into its original state. Or overcoring is a method where you attach strain gauges or deformation sensors to a rock, and then they release the stress that's surrounding the rock mass, measuring the associated deformation to understand the stress that the rock used to be. So these are all displacement-based measurements to back out the stress. These are kind of limited in the distance that you can achieve. I'm not sure if you guys see my mouse. Do you see my mouse? Oh, okay, good. Yeah, so these are kind of limited in the depth range that they can achieve. So more typical in boreholes that can reach greater depth, people tend to also use hydraulic fracturing. So hydraulic fracturing is a method where you keep injecting the water until the rock fractures against the minimum principal stress. So you cycle the pressure many times to kind of observe the opening and closing of the fracture in order to understand what pressure was necessary to open these fractures. So that becomes kind of a direct, probably the most direct measurement method we have currently. Another popular method in boreholes is actually what we focus on today is to look at the wellbore shape or images in order to identify regions that have collapsed. So these are wellbore failures that tell us something about the stress magnitude. So this is going to be the focus of today's talk. So how does this work? So I'm trying not to get too much into the details of the technology, but essentially the idea is that when you have a pre-stressed rock, due to the stress in the earth, stress state is homogeneous. So these lines are describing the trajectory of the principal stresses. If we're talking about a vertical hole, this would be the maximum horizontal stress, SHmax, or the minimum horizontal stress, SHmin. And if you take out the borehole rock that was supporting the load, the stress gets perturbed as shown by the contours that are no longer uniform, like the top case. So the stress concentration introduced by taking out the rock gives us is dependent on the far field stress. So it helps to kind of analyze what the state is around this borehole. So Kirsch has derived this formula that tells us about what is the hoop stress, the stress parallel to the borehole wall around this well. So the equation is shown in this blue figure, blue box, where the hoop stress is a function of the far field stress, and then it has a dependence on theta, which is a measure of the location relative to the orientation of the SHmax. There are also some additional terms that modify the stress, but the important thing to note is that if you plot the hoop stress variation around the borehole, it's going to create some kind of sinusoidal pattern as shown here. And if this stress exceeds the rock strength, the borehole will fail. I apologize. I remember that this is a slide I typically expect that I can use a stylus pen, but today I can't do that. Well, maybe I can do that with my mouse. Yep. So say if your rock strength was limited to here, then parts of the borehole exceeds the rock strength, and therefore you're going to get failure. And that's why you get the borehole breakout features. Okay. So if you can evaluate the rock strength of the borehole wall, for instance, using more Coulomb criterion as shown here, you can back out, you can infer at what point of the borehole this hoop stress sigma theta theta exceeded the rock strength, and then therefore you can back out what the SHmin or SHmax magnitude was that caused these failure. So this is a technology that's existed for quite a while, since the 90s, and is repeatedly used in the industry. And the advantage of this technology is that if you can combine it with hydraulic fracturing, theoretically, you can determine the complete stress tensor. Also, measurements, essentially the imaging, can be done in deep boreholes. So while the civil engineering methods on the left was kind of limited to proximity of excavation, you can access much deeper depth, which is of interest to geological engineering. Also, you can utilize the width of the breakouts to uniquely really define what the horizontal stress magnitude is. But there is a limitation to this, which is essentially highlighted here. Breakouts and drilling-induced tensile fractures don't always form. I forgot to mention, but sometimes this sinusoidal pattern can also go down into tension. Sorry for my mouse drawing skills, but you know, this is where the breakouts form. Whereas if the stress condition is right, you can also create tensile fractures that look like this. Okay, so we won't focus on that today, but the important thing to note here is that you have to have the right stress magnitude. Essentially, the stress has to be low enough, or sorry, stress has to be high enough, and also the right rock strength, low enough rock strength in order to create these features so that you can analyze stress. But if the condition is not right, if the stress is too small and the rock is too strong, you won't get these features. For instance, as you can see in this middle section or in the bottom section. So you won't get any information about stress. So the proposed technology is that we want to overcome these limitations. I also note that these imaging tools have a limited temperature range, so that also determines the maximum depth that you can do these kind of analysis. So what is the thermal breakout project? This essentially started from our partner RISPEC's previous, what the insights gained from RISPEC's previous project. So what they were trying to do in a previous project was to melt rocks using borehole tools in order to seal a borehole. This is a quite interesting idea. And they were developing downhole tools to do in situ melting of rocks. They were successful melting the rock, but they also realized that the heating caused many fractures around the borehole, which you can kind of see by the rough edges here. I think the center portion is the molten rock, whereas the surrounding is the brittle fracture that formed around the borehole. So, and they noticed that heating induces a significant amount of thermal stress. And this led to the idea that maybe you can use this and for this project, it had a detrimental effect because they were trying to seal the borehole, but they were introducing fractures around the borehole. So now they thought about using this to intentionally create breakouts. So the way the concept works is fairly simple. So for instance, the first gray line on the bottom may be that hoop stress variation around the borehole, which does not reach the rock strength. So the rock strength limit is shown by this dashed line. But if you heat the borehole and create an additional hoop stress due to the thermoelastic stress, you can raise this entire sinusoidal curve so that the maximum hoop stress reaches this rock strength and therefore create breakouts. So this equation on the top right is the Kirsch solution that only that applies for just a maximum value of the hoop stress. But as you can see, you can relate the amount of hoop stress you get with the amount of temperature, as long as you have the proper thermoelastic properties and elastic moduli and Poisson's ratio. So this gives us an idea that if we can measure the delta T that is required to create this breakout, we can also back out what the stress magnitudes were that created this sinusoidal curve. By the way, if you have questions in the middle, feel free to stop me. I see this kind of as an informal session, so please feel free to stop me. I hope this makes sense. Fairly simple, if we don't see breakouts, why don't we cause them by ourselves by heating the borehole? So does this really work? So in the project, we had some early experiments and field studies that tried to prove that this actually, this idea can work. So first is the shaped core experiments, which was done by Seiji Nakagawa in Lawrence Berkeley National Lab. So what happens in this experiment is they use this rock sample that has a particular geometry with a narrowed center section. I'm sure this is similar to the dog bone shaped experiments that you guys have also been doing in the past. But the reason why in this case they do this experiment is not to create tension, but actually intentionally kind of create a stress concentration in the middle that is similar to the curvature of the borehole. So by loading axially, they can cause kind of a simulated hoop stress at the side of the rock. What Seiji also did is they know that they can actually load the rock until failure forms to simulate. So this originally was done by Nakagawa and Rasui and Chevron, where they were trying to kind of simulate a breakout failure by loading the sample axially. Okay, so what Seiji did is they loaded until they put some axial stress, but not enough to create the breakout, and then he spot heated the surface of the rock to kind of simulate that thermal stress that we are trying to create in a borehole. He also has AE sensors embedded in the piston so they can monitor the activity. So this is kind of like the summary of what happens in the experiment. Red is showing the axial stress that is increased in steps, and then these background red is the timing when the heating by the infrared heater lamp is occurring. So what you can see is that, so if you basically increasing the axial stress is like increasing the hoop stress. So what you can see is that when the axial stress is low, heating does not cause anything because you don't see any acoustic emission occurring. But then once the axial stress reaches a certain level, heating does cause failure analogous to a breakout and associated acoustic emission. And actually you can see that in test 3, you see this kind of a simulated breakout happening and the spalling of rocks that you see on accumulating on the bottom. Okay, so what this proves is that at least it's a proof of concept that the heating induced rock failure is a function of the background stress level. So identifying the amount of heating that's required to cause this becomes a measure of stress, or we can infer what the stress magnitude is. So occurrence of compressional failure due to heating is controlled by background stress. So our colleagues at RISPEC also tried to do a proof of concept study in an underground laboratory, namely in Sanford Underground Research Laboratory. This is a abandoned gold mine, I think, that is now extensively used for many underground laboratory experiments. So in the recent years, there was a Kismet project that tried to do hydraulic fracturing in this mine, and right now there's an ongoing EGS collab, which is aimed at creating hydraulic fractures and under in-situ conditions for geothermal energy studies. So this is what the 3D structure looks like. You can see that it's quite extensive, and the region where they're doing the test is the orange spot you can see on the bottom. Okay. And you can, this is what the site looks like. The advantage of this location was that I think some of you might remember that this is actually where the DoCell project was proposed maybe 10 to 20 years ago. They were trying to create an underground laboratory there for geotechnical engineering. So there were actually boreholes already existing. So we could take advantage of it and try to test the concept. So what they did is, the colleagues at Respect call this like a garage science tool, and it's very simple. They just have a heater in the middle and several additional components to stabilize, and then they'll stick this in the borehole to see when the breakout, and also monitor the temperature. So you have the heater element temperature that reaches about 1000 degrees. And then the radiation heats the rock, and the rock temperature is also rising slowly over time. Can you see the screen that just switched? Okay, so after heating, this is the camera that they use to look at the borehole. So now we're going into the borehole. Sorry if the volume is too large. I hope you can adjust it. You can see the tape measure that's basically indicating the bottom of the borehole. Sorry, it's stuck right now. It's about to advance again. And you see the end of the borehole there, and that's where. Okay. So I stopped it here because the camera is going to start to get foggy. But what you can see here is that you see these regions on the side of the borehole where it actually created a breakout.
Stresses are, I think we're like
it's now rotating. Yeah, so it becomes foggy.
Like this.
Yeah.
But quite interesting. So this shows that this idea that thermally induced stress causes breakout do actually work. So this is 4 locations that they tested. You can see diametrically opposing breakouts forming in the 4 o'clock and 10 o'clock direction. So it means that these are indeed breakouts as we expect, as we see in typical boreholes. And we can also see rock chips falling that is similar to what is produced in boreholes that breakouts that we know. Okay, so now I want to get into some laboratory experiments that we actually did in UW-Madison. So we proved that this can actually happen. Conceptually, it works. But can we use it as a stress measurement tool is a whole other story, because you have to achieve precision to, you have to have enough, substantial, good enough precision to make it, call it a stress measurement tool. So the experiment was carried out by our postdoc, Maciek Treciak. So what he did was so we used our True-triaxial apparatus that we have. This is the one that Professor Betzalel Heimsen designed, I think in the 90s. And so the gray frame that you're seeing is the load frame that applies the vertical stress. And then there's a pressure chamber where you can insert a prism-shaped sample, so you can load from the left and right, and also top and bottom on this bottom left figure. So that way we can apply a true triaxial stress state. The samples are quite big, 5.5 by 8-inch prisms, and we use Niagara dolomite and Berea sandstones to do these tests. We also have acoustic emissions embedded acoustic emission sensors embedded in the platen so we can hear the rocks break. And also in the heated test, thermocouples that are embedded so we can monitor the temperature. So what do we do in this experiment? What we do is, of course, first we want to just do a room temperature experiment because we want to establish a baseline of when breakouts form in this laboratory borehole. Oh, I forgot to mention, but this is a 0.75-inch borehole. So just like in a normal true-triaxial test, first you increase all the stresses the same amount. You hold one of them, and then you increase the other two. You hold the second one, and then you keep increasing the maximum stress. In our case, that's the SHmax. That's the SHmax applied in this direction until we see signs of rock failure. So on the top is the principal stresses that are applied from the equipment. And in the center, these are now converted into the borehole cylindrical coordinate system. So now we see that the red one is the hoop stress that we're interested in. So if we look at the acoustic emission activity, we see that where there is a rapid increase in acoustic emission, which probably signifies when the breakout happens. So let's see if this works. All right, so this is a movie showing how what the borehole looks like as we increase the hoop stress. The S theta right here is the hoop stress. So right now we're just seeing dust particles and a little bit of grains kind of plucking out of the surface. But as the experiment proceeds, we're going to see spalling of the borehole surface. It's supposed to happen pretty soon. You can already see the rock fragments kind of piling up on the bottom. Sorry, I don't have the timing memorized. Okay, so you see now there's a lot more falling down, and you can start to see the surface changing morphology due to the breakout formation. All right. I don't see a progress bar where I can control this. I'm sorry. Okay. So what you might notice is that when do you know that the breakout happened? Because it's not like all of a sudden the whole thing collapses. It's quite subtle because you start by these grains plucking out, and then gradually the pieces get large, and then gradually you start to see this borehole surface changing. So, sorry. We had quite a bit of discussion on how to use the acoustic emission to identify the onset of breakout. The acoustic emissions locate fairly nicely. So this is as we expected. It forms at where the breakout should happen. I won't get into too much detail today, but essentially what we noticed is that we can classify the acoustic emission into source types, C for compressive, S for shear, T for tensile events. And it's really the onset of the tensile events signifying kind of the splitting open of the rock fragments that corresponds with the onset of breakout. I can talk about this more in detail if interested, but I think in essence, that is what we rely on right now to identify onset of breakout. So the first problem occurs when we compare the hoop stress when the borehole breakout occurs. So on the top right, I'm showing a kind of a table of stress conditions when the failure occurs. I just want to point your attention to the one surrounded in red. That is the hoop stress at failure. We call it BCS, standing for borehole compressive strength. The top three is for Berea sandstone, bottom for Niagara and dolomite. On the left is the rock strength constrained by conventional triaxial tests on a cylindrical sample. You can see that the UCS is about 70 or maybe around 250. So you can see that the rocks are actually failing at least factor of 2 stress, well, not at least 2, but significantly higher strength, because UCS here is 70, but then it's failing at 130. For the dolomite, it's around 250, but it's failing at 400 megapascal. This is actually approaching the maximum stress we can apply. So this is a big problem for us. It turns out this is somewhat a known effect. So it has been determined, understood that strength of borehole walls becomes stronger as the borehole gets smaller. You can understand this as a typical size effect that's kind of empirically known. Some have also tried to use fracture mechanics to explain this, but the essence is that even for boreholes that are 2 centimeter in diameter, the critical tangential strength, that's the hoop stress at failure, divided by the uniaxial compressive strength, can reach is about a factor of 2. So we are not 100% comfortable with this discrepancy, but at least if we can say that this is a known effect, and we can understand that these numbers that we recover from the experiments represent the strength of the borehole, we can apply this number when we do a heated experiment. So how does a heated experiment work? Very much the same as the previous room temperature experiment, except that we don't keep increasing. Let me get rid of this zoom panel. Okay, we don't keep increasing sigma h. We stop increasing it here. And of course, that's because we want to induce a breakout by heating rather than just external stress. So after we keep the maximum horizontal stress at a constant level, now we start heating the borehole, and this is the temperature data registered by the thermocouples we have. How do we use the thermocouple data? If we plot the temperature profile as a function of distance, so each of these thermocouples are at a different distance from the borehole, so you can kind of get a temperature profile as a function of radius. And with the exception of this one sensor, it follows a quite nice trend. So we have models to kind of fit this data, and that way we can extrapolate and understand what the borehole stress, borehole temperature is. So if we use that information, that gives us the delta T at the temperature of the borehole, and with the measured thermoelastic properties, we can calculate the additional stress we are applying due to the temperature change. So on the bottom, now you see how the stress is changing during the experiment, the hoop stress, which is due to the loading at the beginning, and then also the heating that happens towards the middle. If you compare this hoop stress variation with the AE occurrence, again, we can see how the acoustic emission activity picks up quite rapidly. So that tells us, again, by just looking at the tensile acoustic emission activities, that allows us to identify where the breakout, where we can call as the timing when the breakout happens. So of course, if we know when that happens, we know what temperature it was at that point, and therefore we know the thermal stress, and therefore we know what the hoop stress was when the breakout formed. This is just to show that the acoustic emission activity during a heating experiment is actually quite similar to a room temperature experiment. The top right here is the image that I already showed. Bottom left is when things are heated. You see a little bit of difference in distribution, probably due to uneven heating or rock heterogeneity. But basically, acoustic emission characteristics are the same, so we can use the same logic to identify the occurrence of breakouts. So once we know the timing at when the breakouts formed in the heated experiments, we can simply flip this equation around, solve for the sigma h in order to kind of estimate what the sigma h value is, knowing the delta t at borehole onset of breakout. So this is where we also run into another big problem. So I said that the size effect, we can take in, we can sort of empirically address the size effect by just saying that even though these hoop stress values do not agree with the UCS that we measure from cylindrical samples, this is whatever stress it takes to create a breakout in a borehole. So we even if we take that empirical approach, what we find is that we tend to underestimate the far field sigma h. We know exactly what stress we applied. Sorry, it's on the horizontal axis. We know exactly what we applied, but what we predict from our lab results tend to underestimate the SHmax that is applied. So we attribute that to the strengthening of the rock due to the intermediate stress. So Moore Coulomb criterion only looks at sigma 1 and sigma 3, but it's been very well known for decades that the intermediate stress sigma 2 also has an influence on the rock strength. Indeed, if you look at the middle figure again, especially when you heat, it's not only the hoop stress that is increasing, but you're also increasing the intermediate stress quite a bit. So we think that's the cause of why the borehole appears to be stronger, and therefore we need to modify our approach and use a true triaxial strength criterion. So we did this approach. We did this. I won't get in too much into the detail, but basically what we did is we have our laboratory data of strength from cylindrical samples that we tested in a conventional equipment. We can use this to constrain, for instance, a Nadai criterion or Mogi criterion. You can see that the fit to the data is quite, good. So we thought we were very confident about how these criteria will allow us to predict failure. But what we still notice is that there is a discrepancy. So when we compare the octahedral stress values, for instance, in a Mogi criterion, for breakout tests, that's done in a true triax setting, versus regular experiments, conventional tests, conventional triaxial tests, we see that these data populate in a different group. Namely, the conventional experiments show a weaker prediction compared to what we observe in the borehole. So this tells us that even though we can constrain criterion from cylindrical samples, that cannot be applied to the borehole geometry. Actually, this is somewhat known from past studies. This is a study from Song and Heimsen, 1997, which does a very similar comparison to what we did here in this previous plot. they found out that agreement between a triaxial test and a breakout test depends on the rock type. So left column is westerly granite, right column is Berea sandstone. They understand that Nadai criterion works better for high porosity rocks, whereas Mogi criterion works better for westerly granite. There's a whole lot of discussion that goes on about whether this comparison is valid or not. But I think what this tells us is that even if we can constrain true triaxial strength, it's not very readily applicable to the borehole setting, especially when you're trying to back out the stress. So the summary from this lab testing is that phenomenologically, we are successful in creating this thermal breakout, and we have first order success in kind of inferring what the far field SHmax magnitude is. But there's certainly effects that we are not totally comfortable with yet. One is the size effect, which we could only address empirically. And then also the fact that this true triaxial criterion that we constrain from cylindrical samples do not really apply to the borehole geometry. Applying true triaxial criterion to borehole, we're definitely not the first ones to do it. It's been studied again for decades, but most of the time they use it in terms of identifying the safety limits and drilling, whereas we are actually trying to precisely determine the stress. And it turns out, I think it's fair to say that we don't have good enough knowledge about rock strength in order to make the reverse happen of estimating stress from borehole deformation. Finally, I just want to mention about some ongoing things. So as I mentioned, we are in year 3 of the project. So what our colleagues in RISPEC called garage science tool actually works quite great in producing field thermal breakouts. But we're actually also, with the help of Integrity In-situ, designing a prototype tool, which is a little bit more refined, better temperature measurement, better temperature control capability, and also in-situ acoustic monitoring, so that we can identify the onset of breakout in the field. So that is designed and I think underway in construction. And we hope to take this to the SURF Underground Laboratory again to test our concepts. Particularly, we're going to go to a little bit shallower level. The 4850 level is now occupied by the Fermi Lab, which is trying to shoot neutrinos from Chicago to South Dakota and detect it in the underground lab. So that's a major project that's going on there. So we are now kind of kicked out of the 4850 level, and we are at 4100 level. But the advantage is that this is where the EGS Collab is also project is also doing extensive hydro-shearing experiments. So we will be drilling boreholes here, so and creating new measurements as that can provide insights for them, as well as receiving information from EGS Collab. It's a slightly more tight spacing, but the drilling equipment can still fit. So, whoops. Sorry, I didn't know that there was a movie here. Let me keep going. But what we will be doing is that we will be drilling vertical and horizontal wells as well as a diagonal hole, because the borehole that's not oriented with the principal stress gives us some information about how the breakout occurrence tells us the ratio of the principal stresses. Probably shouldn't get into too much detail on that right now, but that's the activity that's going to take place hopefully within the next half year, I think. so we can test this method of creating thermal breakouts and inferring stress from this new field tool. Okay, thank you for your attention. I think I'll stop there for now.
Thanks for the talk, Hiroki. That was very interesting. So if anyone has questions, we're going to do it where you can unmute yourself and ask Hiroki your question.
So I have a question. Thank you, first of all, for the talk. It was very interesting.
Yes, thank you.
Do you think like that's because like you were presenting like that, you have the discrepancies between the lab experiments and the actual borehole predictions.
Mm-hmm.
Do you think there might, like, what might be the extent of the influence of the fluids in the borehole, like the mud that is used, on the strength or like maybe changes of stress or the temperature in the actual borehole versus what you can simulate in the lab experiment?
Yeah, I think that's certainly going to be additional complexity when we go to the field. Right now, these laboratory experiments, we're just dealing with dry rock and no fluids. So, you know, it's supposed to be more simple, but we are already struggling quite a bit. So, yes, you know, if you're in a clay-rich formation, for instance, I can easily imagine, as you said, fluids will complicate the rock behavior, right? And also poroelastic effects. Heating will undoubtedly increase the pore pressure in the rock. So those are probably the challenges as we apply to more realistic conditions. But I guess what I can say is that yes, I think getting the magnitude right is going to be quite challenging. But at the very least, we can still give stress orientation information where it was not available. So I think that is definitely added value that could be provided by technology for sure.
Yeah, I mean, I agree. Like the orientation itself, like locally, will be very useful,
Mm-hmm.
especially in the areas where you don't have, you know, a lot of information from measured breakouts, like let's say classic breakouts.
Right. Mm-hmm.
Thank you.
Yep. Thank you.
All right, Hiroki, there is a question in the chat from Bo Luo. On slide 29, he is asking how you get the value of the Biot coefficient for the thermal breakouts and traditional breakout.
How do I get the value of? Sorry, could you repeat the question? Oh, okay. I on slide 29, how to get the value of BO coefficient? I see. Is this is BO coefficient, right? Yeah. So
appears to be so. Yes.
If I understand correctly, this is for when you have pore fluids, right? So right now we don't have pore fluids, so I don't think BO coefficient is needed for at least our interpretation. But yes, as we move into water-saturated rocks, definitely the pore pressure change is going to also be a function of the poroelastic parameters like BO coefficient. So that's something we have to measure or estimate if we don't have the lab measurements, if we want to incorporate in the analysis. Yep. I hope that answers the question.
I have some questions.
Sure. Yes. Hi.
Thank you so much for your talk. So, oh, well, okay, sorry, Fred. I think I just saw you raise your hand. Anyway, I will go first. Okay. Can you just explain, I probably missed that. Can you just explain where your heating source in your experiment?
Yes, I didn't explain that. You're right. Well, it was basically nichrome heater element, where you just apply voltage. Yeah, basically we just put it inside this heater inside the borehole and put a constant voltage, and the temperature of the heater increases, and then the radiation also increases. So most of the heating is done by radiation, actually.
Okay.
Yeah.
Okay. And I had some question, but okay. No, I think that's the main question. And then I had some question about the SAGE's result. I was just a little confused, but I think maybe it is, I think you have an acoustic emission only during the heating time. Am I right?
Right. So the blue is the cumulative energy from acoustic emission. Oh, I see. It's hidden. I'm sorry. This is acoustic emission cumulative energy.
Right.
So you see the increase in the blue data. That's occurring only during the heating.
Yeah, but I think, well, so I think, okay, maybe, so, okay, you have a, particle bar for the heating time. So that's the only heating time. So after that, for example, the third one, you have a, acoustic emissions during the heating, but then it cooled down before you dump it up to the next stage of the stress level. Am I right?
Yes. Mm-hmm.
Okay, I see. Now I understand that.
So
another thing, yes, okay.
Yeah, I don't remember if he has well, I think he has the temperature measurement too. And most likely the second time he sees acoustic emission, that occurs at a lower temperature, I think.
Okay.
That's not expressed in this graph, but yeah.
Right. Now I remember my second question about your lab settings. So your measurement of the horizontal stress, or you have basically the polyaxial applied load. So once you start heating up, are you still trying to keep the load constant?
Yes, it's stress controlled.
Okay. So basically the macroscopic stress is constant. Yes.
Right. I forgot to mention, but there's a servo intensifier on the backside around here, and that's controlling the 3 stresses constant.
Okay. Okay. All right. Yep. Thanks.
Yeah, I have a question.
Yep.
Hi, Hiroki. Enjoyed your talk. Thanks for that. I actually have 2 questions, but one is if you would speak about the duration of heating and heat diffusion into the rock, and if you take that into account in terms of your analyses.
In the True-triaxial experiments.
Yeah, sure.
Yep. Where do I? Oh yeah, we got to go to the heating experiments. Yeah.
I mean, so, specifically, I guess I'll just be more specific. The temperature in these equations is assumed to be homogeneous, and how close do you get to a homogeneous temperature distribution in the sample?
Actually, we are solving the diffusion problem. So the delta T is the temperature at the surface of the borehole wall. So there's some literature on why that's the only temperature that matters, but there's a Voigt and Stevens, I forgot the year, but they do a very detailed analysis of how the thermal stress is only dependent on the surface temperature. So our goal is to just extrapolate and understand what the temperature is at the borehole. So we use these multiple thermocouple measurements. You can see going from 600 seconds, 700, 800, 900. You see how the temperature distribution keeps going up. And we fit this using a thermal diffusion model of how there is actually a constant temperature, constant increase in heat flux is the right way to describe it, actually. That's the only model that can fit this data. And that's how we kind of gain confidence in our understanding of the spatial temporal diffusion of heat. And therefore we can extrapolate what the surface temperature was, because measuring the surface temperature is quite complicated, right? How do you install the thermocouple? That's a very difficult problem. So our thermocouples are still inside the rock, and we infer the surface temperature from kind of the profile of the temperature. I hope that makes sense.
Yeah, so I'm also curious about, thermal expansion in the axial direction too. Do you take that into account?
Yes. So I again didn't go too much in detail on that, but yes, the thermal stress actually does create the same. The temperature change creates the same thermal stress in the axial direction as well. So that's what you see in this blue data right here. You see the sigma ZZ also increasing together with the hoop stress. So because the intermediate stress is increasing, that's also most likely increasing the rock strength. That kind of tells us that using UCS is not appropriate.
Right. So you take all that into account in your predicting and checking failure strength. That's
right. So we tried, but it still does not work so well.
Yeah, I get you. Yeah. Right.
Yeah.
Okay. Yeah.
So we teach about rock strength, and more Coulomb takes you quite ways to predict many things. But through this project, I just learned how little we know about rock strength.
Yeah, that's true.
Yes.
I have one other question, and that was in your acoustic emissions. Can you look at magnitude or frequency of the emissions to kind of distinguish between microscopic fractures and kind of more larger fractures that lead to spalling, kind of or shear fractures, in the sense of what in the natural borehole? Is that possible, or are they all pretty much the same magnitude AE?
Yes, we tried to do that. We also looked at how the B value changes and percentage, fraction of opening versus tensile, and also magnitude, as you said. But the information that gives us the most sharp increase in the signal is really the cumulative energy. Maybe we're not trying hard enough, but I guess the short answer is it was difficult. We tried, but it was difficult. And especially this is Berea sandstone that produces the most acoustic emission. The other dolomite I didn't talk about today actually did not give us so many acoustic emissions. So it was it made it quite challenging. Yeah.
No, I acknowledge the great difficulty. These are not simple experiments. I know they take a lot of work, and it's really impressive. It's really nice. I guess I'll just ask one more brief question, and that's about, in borehole stress measurements, we often just kind of assume a Andersonian stress model. And but in this case, if you can get this to really work well, you could drill, like in your situation, drill boreholes at different orientations and try to maybe also get the stresses, the principal stresses, that is, the true stress state, rather than just the vertical and horizontal stresses. I know in many cases the vertical and horizontal stresses are the principal stresses, but that's not always the case, right?
Yes, you're absolutely right. In fact, let me try to get there. In the some results from the EGS collab may suggest that the vertical stress is inclined. So, those are things that we might be able to address by looking at this. Sorry, it takes a while to get there. Yeah, so we're actually precisely kind of trying to calculate what orientation would give us most information about the orientation and the ratio of vertical to SHmax. And you know, Dan Moose has, you know, he's from GMI. He's helped us quite a bit, kind of getting this analysis right. I'm gonna dare myself to actually explain this now. So this is a plot of a borehole deviation. So the angle of the borehole versus SHmax, and the colors are showing what angle will the breakout form. So depending on the magnitude of the SHmax, you know, for instance, if you drill in a certain orientation, the color changes. So the orientation of the breakout changes. So this is kind of a classical analysis that GMI does, but we're trying to, because at least our tool can give orientation of the breakout quite well, even though the magnitude is challenging. We're trying to see if we can achieve that kind of analysis in this inclined borehole.
Yeah, that's great. Yeah, thank you.
Thanks.
All right, so there was one more question in the chat from Deborah Martogi, asking if you had considered relating the number of AE counts to characterize the development of the fractures. For example, is there any unique AE character when large fragments are observed?
Yes. Let me get to that slide. Here you go. Yeah, so we were really trying to do a lot of advanced analysis with AEs to really try to help identify when this breakout happens, as you said. And so far, the best information we've got is when you separate acoustic emission into a compression type or a shear or a expansion, a tensile event. It's the onset of the tensile event in green here, right here. Especially when we compare with the video, that's when really the large fragments start to fall. And that kind of makes sense because before macroscopic failure, there might be small scale shearing or compression happening in the rock. But then when the big pieces falling down, you know, something is opening up, right? So that's why, as of now, our best information is really the onset of tensile events that tells us when the breakout is actually happening. But I guess I would say that, you know, in the field, we can't do this kind of advanced analysis. So that's why we also, you know, try to compare this advanced analysis with kind of a simple information like energy, as I show in black here, which can be captured by downhole tool. So we won't, because, you know, locating acoustic emission, classifying into source types downhole is quite expensive computationally, and you need a CPU down there. So we want to only use simple information like energy in order to identify the onset of breakout. So that's why we're, at least in the lab, we can compare to see how we can calibrate the way we analyze this.
All right, thank you, Hiroki. We are at past 6 o'clock, so I think it is time to wrap up the meeting here. But I was very interested in this presentation and would like to thank you again for meeting with our ARMA chapter.
Yes, of course. Thanks for inviting. I really enjoyed the discussion. Yes, I hope this was enjoyable a little bit.
Great job, Hiroki. Nice seeing you.
Oh, thanks, Corey.
Thank
Take
you.
care.
Thanks, Hiroko.
Bye.
Thank you.
Yep, thanks, Judy.
Thanks, Hiroki.
All right.